Hi, I'm David Greenberg, and welcome to the 18th episode of the Machine Learning at Helmholtz-Zentrum-Gestalk seminar. We have a really interesting paper today, going to be presented mainly by Marcel Nonnenmacher from the Model-Driven Machine Learning group. We've touched on a couple of the main topics in previous seminars. So one of them is data-driven versus physics-driven modeling of data and prediction. So when we have a sequence of observations, we want to predict future observations, we can use a purely data-driven approach like a neural network that doesn't have a model of the internal dynamics of the system that produced this data. Or we can use a physics-driven approach which may have a lot fewer parameters and may generalize to new data much better, but can be harder to fit and apply to these data sets because it doesn't have the tools and the nice mathematical properties of some of these machine learning techniques. So the current paper asks, could we use machine learning and data assimilation together to come up with a model of the dynamics that produce the data without having any physical insight, just by using machine learning? And I'm going to turn it over to Marcel for some details, the basic setup, and then I think there'll be a few good places in the presentation to sort of stop and take questions and discuss the main concepts and results.
Okay, can everybody see my screen?
Yeah.
Okay. So as David already summarized, today's session is going to be about learning dynamical models from data. So it's going to be about toy models, the Lawrence 96 model that we've seen before mostly. So no one's going to learn global circulation models in this session. But with that, with this restriction out of the way, so the general idea is that you have a system. Like here in the top panel, we have a simulation of a 40-dimensional Lawrence 96 one level model over a certain amount of time steps. And from such data, we want to train a surrogate model using machine learning that behaves when initialized at the same state, that behaves similarly. We want it to behave identically, but there's going to be some error. And given the fact that we're going to deal with chaotic systems, this error is going to increase over time. So the top one is data from the original model. Then the middle one panel here is a rollout from the model that we've learned. And then the bottom one is the error. So it's small increases. The idea is going to be to have the error as small as possible for as long as possible, which is going to constitute a good model. Now, we have talked in the last session in the context of parameterizations about how to transfer information from an existing model onto a machine learning model by training on the data. And there it was just that you just generated data from the dynamical model, the physical one that you wanted to learn, and then you just trained a neural network to predict, for instance, the next state from the current state, and then you can check how it works. What the results are, you might have to use a deeper neural network, you might have to train longer on more data, but essentially this should be straightforward. Now, what the authors in the papers of today, what they concern themselves with is the more direct applied case where there is no ground truth model necessarily, but there is data. So the surrogate model here in the middle panel was learned on data from the true model, where 50% of the data was missing and the rest was noise corrupted. So you can't directly train a neural network on that data sensibly and expect it to work very well. So you have to do something before that. And today will be all about what you have to do, or one approach of what you could do.
Sorry, why can't you train just a neural network on noisy data?
On noisy data, you could. Depends on the noise level. Especially if you do one step to the next step predictions, if you have a lot of noise on the data, if you don't have any noise and you know that the data comes from a smooth simulation, right? You would expect to be able to very well predict the next state, right? But if you, on individual consecutive time points, have a lot of noise, the target for the neural network to train is going to be drowned by the noise, unless you have very, very specific noise structure that you know. What's the much bigger problem, however, is when you have missing data. We're going to see this a bit in a specific case where they just try to initialize the algorithm that they're actually going to develop here, which is a multi-step algorithm, by initializing it by a neural network that's just trained on the data with holes that they then just linearly or cubically, I think, interpolate. And then you can see the results of that.
Thank you.
We'll get to that in a moment. Okay. So this is the main paper for today. We're going to talk a bit about a follow-up that extends this in one or two cool ways. But we're mostly going to focus on this paper today, combining data assimilation and machine learning to emulate a dynamical model from sparse and noisy observation. And again, the sparse and noisy observation is the key point. All of the authors, interestingly, are professor rank, so it's quite an interesting equipe. So, as they say, like, we've had these interesting developments in machine learning, in particular in the subfield of deep learning, that have demonstrated that with enough data and enough compute power, you can learn very, very complex spatial-temporal processes. And there have been several studies that try to apply this now to earth science models, mostly in the scenario where you have perfect access to data, like you have a simulator, you can simulate training data from it, and then you learn that. For really noise corrupted data, as it's often the case, this hasn't been done that much. The one thing you can think about is the reanalysis data that comes from IFS systems. You have an IFS system, but what this IFS system integrates in practice are highly incomplete data, satellite images of projections of the full system state onto certain surfaces, but not the full system state and not without any noise. Now, if you wouldn't have an IFS model that you could use to integrate that, to assimilate that data, how would you come up with it from such noisy data? And the main way that they're going to go about this is to combine this data assimilation, which allows you to estimate a state trajectory from incomplete noisy data given a model, and then that state trajectory that they have estimated, they will use that to improve the model. So let's quickly go into the setup of the problem. So the main thing that they're going to assume, and this notation nicely is going to stick throughout the papers that we're going to look at today, there are some observations. They're going to be called Y. And then there's some actual system states that are not observed. In machine learning, we call them latent variables, X and Y. At a specific point in time, they use K as a time index, is obtained by taking the actual state X and pushing it through an observation operator H. It can be a linear operator, and it's going to be for most of the, actually for all of the experiments today, which just subsamples a bunch of positions from the state, and then to those that it's subsampled, it adds Gaussian zero mean noise. So this is how the observations come about from the system state. There's some covariance matrix or that noise that we had. Usually we assume it's identical. Like every pixel of our observation has its own private. And then we assume some dynamics. So these states, they're not random. There's a temporal evolution given by some differential equation. And then by integrating that differential equation over time, we go from one time step to the next. And the thing that does this state updating, we're going to call funky G of X. So from xk to xk plus 1, there's this operator. And this is going to be the thing that we want to learn. So this, once we have learned this, we have kind of captured the dynamics. There's a thing between this paper and the next paper in particular, whether or not the update is stochastic or not. In the simpler case, you just assume that the dynamics of what I call the latent variables, these actual system states X, if they are deterministic or if they are stochastic. If they are stochastic, you also have to learn the distribution of that noise. If they are deterministic, things are a bit easier. So what they do in this paper that we will be mostly talking about is they assume that this operator that does the state update is going to be the old state, yeah, plus some update and no noise. And the update is going to be given by a neural network that has some weights. So the weights are for all of the weight matrices in all of the layers of the neural network. So, and from the figure that I've shown you before, figure 6. So this is obtained with the original G, the state update operator, and this is obtained with the learned one. With a certain setting of these weights W that we obtain from learning. Right? So once we've gotten a good set of W, we're fine. Now how do we obtain this? Well, if we had the states, what we would do is we would, from a certain state at a certain point K, we would apply the operator I times, and then we want to have predicted the actual state I times into the future. There's a sum, you can do this for different rollouts. For most of this paper, they just do I equals 1 for the next state. So from xk to xk plus 1, they apply GW, and then they minimize this with a squared error, which is possible because GW is a neural network, and you can take the derivative of its output with respect to W, given its input. And this is a very standard noise. This mean squared error essentially assumes that this noise here is Gaussian IID with a certain variance. Now, it's not IID. This thing here marks a Mahalanobis distance. So the mean squared errors between different dimensions of this are actually weighted by some matrix. Here's the definition of this, by some matrix P that we're going to get in a second. Okay, so this is how, if you had the sequence of states, how you would actually get the weight matrix of this neural network that optimally predicts the next state. And if we had the sequence, we would be done now. We could train this directly, and we're going to see one test application where they assume that they have these states directly and how well it works. The main problem is if you have noisy, incomplete data, you don't have the X's. What you have is you have the Y's, which are subsampled and noise corrupted. Now, how do you get that? Well, there's data assimilation, right? So data assimilation is essentially the task of, given a incomplete noise corrupted observations, sequence of observations, and a model, how do you get actually the states? And the way this works is, if you have a model, you create a forecast from a certain analysis state by applying the model, applying potentially some noise, and this you call the forecast. And then what you do is you integrate the observation at the next time point to get an analysis. This is kind of skipped in this paper. Is everybody roughly aware of how this would work? Like how a Kalman filter would update?
I
if
think
there are
one
questions,
thing
raise
that
them now. Otherwise, I'm going to restate this once more, and then I'm going to move on. So the idea is to use a data assimilation technique. In this case, it's going to be a ensemble Kalman filter. In a linear case, it could just be a Kalman filter. If we were sure the dynamics were linear, in this case, they use an ensemble Kalman filter, which works for nonlinear dynamics at the cost of having to run an ensemble. As they said, other DEA algorithms would work, data assimilation algorithms would work as well. So if they have a model, they can get, well, a sequence of forecasts, and from this, upon data integration, a sequence of analysis states given that particular model using data assimilations such as ENKF. And once they have these, they can, for every point in time from the ensemble, so there's going to be a bunch of these states for every time point, estimate a mean and estimate the covariance. And this particular covariance is then going to be used again in the loss for training. So the overall algorithm that they're suggesting is that given a certain state of the model, you estimate the sequence of actual system states using the observations, and then once you have an estimate of these system states, you fix them and you retrain the model of the dynamics. In this case, what you do is you have a neural network for the dynamics. You do stochastic gradient descent or just gradient descent given the above laws. And the idea is that you start out with potentially a very bad model of dynamics, that you get a somewhat poor estimate of the states with your Kalman filter approach. But given that somewhat poor estimates of the states, you can get at least a better estimate of the model. And if you iterate this whole process often enough, you should continuously improve. We're going to talk later a bit about an algorithm that is very, very similar to this. In fact, it's a bit of a generalization. That's called expectation maximization. And that thing you are actually guaranteed, if you do both of these steps correctly, that after each full cycle of this, within the right box, your estimate of your model W is going to be better than before. So the whole thing is iterative. So you start with an initial guess for your model, and then you go through multiple of these cycles until you're done. And each of these cycles is a full data analysis step given the current model, which is expensive. And then you need to train a model, which is to do a full training of a neural network given a new data set. This is the data set in every cycle to train a neural network. So the whole thing is a little more involved than just training a neural network directly on noise-free data. Now, the question is, does this work and is it worth it?
Marcel, if I could just quickly chime in too.
The cycle is a little bit different than we know, for example, from GANs, right? In GANs, we have steps as well. We have a discriminator step and we have a generator step, and they're alternating. But here, when we say step, we mean something different. Is that true?
Yes. So if you did GAN training, which is just training two neural networks pitted against each other, this would be within the ML step. So you optimize W, right, by minimizing this loss, and this loss, which is the loss in W and a bunch of fixed data points, you would iteratively minimize. You would do gradient descent with many steps. And each of these steps corresponds much more to a step of, say, a GAN training than one of these cycles. These cycles, every one of these cycles produces a new data set to train your machine learning algorithm on.
All right, got that.
If I can chime in for a second, Marcel, too. I think it's very interesting to point out the difference between this prediction forecast scheme and some other schemes we've considered, like the schemes in MedNet or Conval STMs and so on, where the neural network will directly take as input several previous time steps, which may contain noise, and then it'll output a future time steps result as a prediction. And it's basically one single process of prediction. Here we're really breaking it into two parts, where instead of relying on multiple previous time steps, we only rely on one previous time step, but then to get the initial state of the system, we rely on multiple time steps in a data assimilation step. So, the estimation of the initial state and the propagation of the dynamics is now two different parts of the algorithm, which are optimized separately, as opposed to this complete solutions that are more data-centric.
Yes. You're also having this double problem, right? That with all of these other approaches, before people assumed that they had usable data right away. While in this particular algorithm, we do have data, we do have the observations, but we first have to clean them up at the same time as we learn the model. So you have to do you have to do two things at the same time, which is why this is a lot more complicated than before.
That's certainly true. I mean, I think if we looked at something like episode 11, where we learned these emulators of physical simulators of particles, there they start with clean data. But then if we looked at something like MetNet, episode 3, they're only working on observations. There is no kind of physical interpretation of the, or here I suppose not either, but they don't learn a dynamical model really. They just map from observations to other observations.
Yeah, this is a big difference in how you interpret and how you set up your model. So here we have a model that's supposed to mimic mostly non-stochastic dynamics, so a differential equation. And the types of models of MetNet, they were inherently black box and stochastic. We do have a noise part, like something that we can use to connect the somewhat clean physical dynamics that we learn with W to data. And this is exactly this observation operator, but this they assume to be known. This is like, how does the current state of the world map onto satellite images? Like that mostly optical process, they assume to be known for now.
Right, okay, thanks.
Known and differentiable, which is a bit of detail, which can be really important, but which they kind of glance over. Well, actually, no, sorry, I'm talking nonsense. For this particular approach, it doesn't even have to be differentiable, which is actually very strong. I was thinking of something else, it's just nonsense. H does not need to be differentiable. It just needs to be known, and yeah.
Okay.
So most of the rest would be evaluating this general approach now, at least of the main paper. So here they describe the setup. So this is the differential equation that we were talking about. It's nothing really crazy. So there's a product here which makes this whole thing behave nonlinear. Exponential decay, external forcing with typical parameters and settings from the literature. So for system size of 4D and F equals 8. So the forcing, you get chaotic dynamics, as we've seen before. So initial errors are going to blow up over time. They produce a sequence of 40,000 time steps from which they're going to subsample and noise corrupt, and from which they're going to learn the dynamics interstate sequence. They do assume that they know the time step of the integrator, essentially by having every integration time step H, they're having one observation. And I point out this would be not known in a real model, so you would have to think about how you set up the dynamics. Because one of the downsides of this approach, where you go from k minus 1 to k, so one step is that the step length has to be fixed. In the next paper, we're going to look at a modification where you directly learn the differential equation, not the whole setup, where you're a bit, not the whole state update function, sorry, where you're a bit more flexible. Yeah. And then they're going to evaluate a bunch of things. The first is the accuracy of the analysis. So you have a model, and given that model, you estimate the states with ENKF. Eduardo, you raised a hand?
Yes, I have a short question in between, if I may.
Sure.
My question is related to the H operator, to the observations operator.
Yes.
In the example, well, when you laid out the model at the beginning, we assume that this operator is just diagonal, if I understood properly, right?
No. So in this particular case, the operator is linear.
Okay.
But it's not a diagonal. Well, it is a diagonal matrix if you allow certain elements of the diagonal to be zero.
Yeah.
I would have thought of it, I mean, this is one way of thinking of it. The other is you start with the identity matrix and then you delete individual rows. And this is also a way of doing subsampling.
Yeah, that was my question, because in the implementation that you were going to explain right now, it seems that this H operator is just a sampling operator, and it's not just a linear combination of the x's, but just yeah, as you explained, that some of the x's are set to 0, right?
Yes. Okay. In principle, this type of algorithm can handle more complex H operators. You can have full linear. In fact, I'm going to quickly show a paper that before this one and the next one that actually learns the linear H operator alongside the dynamics. The EM algorithm, which you might have read about if you read the second paper, it can handle this. Yeah. Here, for simplicity, they just went for a subsampling operator because apparently, well, for this kind of Lawrence 96 system, it's kind of standard to use it.
Yeah, for me, this choice of H is a little bit surprising because, let's say, as someone dealing with observations, I would say that the most simple H model would be just the identity operator. Let's say you assume that the observations are contaminated by observational error, but that's it. That would be the most, let's say, simple and perhaps obvious H operator. But this subsampling sounds to me, well, a little bit strange. Anyway.
I mean, what they want to really make a point about is that it works for missing data. Yeah. And this is when you don't have the identity, but if you have some zeros on the diagonal, I think that this is where it gets really speculative from my side. The idea is to generally mimic that your observations are going to be lower dimensional than the actual system state, right? And this is one thing that you get from not having the right? They have from R to the M to R to the P, and P is usually smaller than the full system state M.
Okay, thank you.
Just quickly, one more note on this. One thing that you really get if you do subsampling and you make it lower dimensional is, even without noise, it becomes uninvertible. And if you had an invertible operator without much noise, you wouldn't need the dynamics to reconstruct the state sequence. You could just, for every k, invert this function and go from y back to x. Yeah. Okay. Back to the results. Unless there's another question, of course. So what they evaluate the quality of the state estimates they obtain with the ensemble Kalman filter given the current model. So the current model goes into estimation of these states, and then I have a mean squared error. Sorry, this is the estimated state. Then I have a mean squared error with respect to the ground truth from the actual simulator. So this is the estimation of the states. And then if you have a model of the dynamics, then from an initial condition, you can then go forward in time to have a forecast. And this is the other thing that they evaluate with the RMS E minus F. So here you start from an initial state and you plug this both into the estimated emulator and the emulator, which is the estimated simulator, and the actual Lawrence 96 dynamics model, and you do this for a bunch of different random initial states and over a certain window that you forecast into the future. And then another thing they look at is the Lyapunov spectrum. So these are the eigenvalues of the dynamics, which in this particular case are important to show that you capture the long-term dynamical properties, in particular the degree of chaos for the Lawrence 96 system. And then for the really long-term stuff, they also look at the power spectral density. Okay. So this is a bit more about the details about how they set up the thing with 30 ensembles for the ENKF. They don't do any of the more advanced stuff like localization, which you need if you have fewer ensemble members in a very high dimensional state. For the neural network, they have something that they call that is called a bilinear layer, which I think they have I'm not mistaken. They have a short sketch. So this is their neural network, which goes from one state to the next. So GW applied to x of k is the estimate of xk plus 1. There's a batch norm layer, which I'm not entirely sure they would need if they were standardizing their data. But the important thing is that they have a convolutional layer that has 3 kinds of outputs. One which just gets forwarded to the next layer, but then there are 2 kinds of outputs, and these can both be multivariate. So you can have an input that is 40-dimensional, and then you can have a CNN with, say, 300 output filters, and the first 100 would be A, and they go on, and the next 200 would be B, and the last 300 would be C. Now, what's interesting about this kind of architecture is that there is a nonlinearity of the type that is non-pointwise. Usually in neural networks, you have pointwise nonlinearities like a rectifier or a 10H function. Here, you multiply 2 different outputs of the previous layer with each other, and then this gets fed into the next stage. And the idea is, this has first been put forward in the context of earth science, I think Fablé et al. In 2018. The idea is that you capture this, at this point, this multiplication, these kind of polynomials which show up a lot in physical dynamical systems. These you can very naturally capture with this kind of architecture. And to see what this does, why this will work, in this particular case, so the CNN, it has a linear matrix when data comes in to produce these. And an affine linear matrix can take the difference between 2 of the inputs, and this would then be the output layer, the output filters B in the network. And this then, if you just learn the operator which extracts 1 state to the left, this, you would have C. So these are these two things here, B and C. And if you then multiply them, you already have the dynamics equation of Lorentz 96. This is a network that is very well suited for this kind of problem. So people are thinking about how to really set up your neural network structures for this kind of dynamical model systems. Here's the exact full neural network. It's not a very big thing. I think they have like on the order of 53 parameters in this thing. Number of layers. No, they have a lot more. Sorry. I was thinking of something else again. So they have this number of parameters, 10,000, which is a little more than I said. Yes, this I'm going to skip for the moment. So this is how this works.
I have a question actually before you go on, because I was very confused by this. You're showing this different layers in the architecture. If you scroll back up to that table, so it's true that with this bilinearity you can capture the structure of the model. But what confuses me is layer 2 has 3 channels of 24 units each, but it has 40 inputs. So if you want to capture, like, you know, the linear terms and the product terms, aren't you lacking enough units to actually do that? Don't you need at least 40 times 3 or something similar?
No, because it's a convolutional network. So you have a ring in the Lorentz 96 case. This is something I might have forgotten to say, but those of you who have been around for long enough might already know, because this model comes up a lot. So this is space, and they have 40 locations, and this wraps around. So this is a ring, and it's a convolutional neural network. So these numbers that David just said, like 72 output filters of the first layer, they are per location.
Oh, I misunderstood that completely. I thought 24 times 3 meant 24 spatial positions and 3 channels, but no, it's 24 channels of A, B, and C.
Yes.
And presumably they all have 40 locations.
So yeah, so this is a convolutional layer, so it applies to every of the inputs, and it has 72 channels, which is absolute overkill.
I see. Wow. Okay, that is really a lot.
Yeah, you could probably get away with much less. I mean, if you're learning the This is a bit of a thing that I oversimplified. So you're learning the state update function, which is the dynamics equation of the Lorentz 96 evaluated through a fourth-step, fourth-order Runge-Kutta, which is how they solve this equation. So it's not just this. It's this evaluated 4 times on itself. But if you were just trying to learn this, which they do in the next paper, then 1 channel each would actually be enough instead of 24. But they have 72 for good measure, I guess. And then they have the rest of the network, yeah.
Thanks.
So this is the outcome, essentially. As we said, the whole algorithm moves in cycles, and every cycle is a full network fit and a full ENKF application. And what we see here is, let's look at blue. The blue curve, this is the forecast error. So with the current model, what you do is you grab the current model after the cycle, you give it a bunch of initial states, and then you start simulating from those, and then you compare your estimated model of dynamics with the ground truth model. And you start with a really bad neural network for the dynamics, and then you estimate a state sequence and you retrain, and the second one, and then over the iterations you get a lot better. There's a bit of noise in the end, but overall the thing clearly works over rounds. One thing they have here in the second is the first Lyapunov exponent. That's roughly the speed at which errors grow over time in this dynamical system, and there's a target for the Lorentz 96 with their settings, which is 1.67. So they not only get the short-term prediction, but also the long-term tendencies of the dynamics.
So there's a question from the Zoom chat.
Yeah.
Zeguo, I hope I'm pronouncing that right, asks, is this a Conv1D neural network model?
Yes. So this does, because space in this model is one-dimensional, you do everything with 1D convolutions. Yeah. So these are the dynamics. One thing that then look at is the power spectrum, the power density spectrum. After the first and after the final, so the first is in gray, the final cycle is in orange. And apart from the high frequency stuff, which they never get, the stuff below roughly 6 hertz, they get very well. So the climate is somewhat preserved. They compare the analysis error. So this is the quality of the state estimate that they get with the true model with that of their surrogate model after. So they do this whole thing to train the surrogate model, and afterwards you can use this. It's in the figure 6. Below, you can use this for full simulations, right? It's not going to be perfect, but if you then do data analysis in an applied case, like you want to do actual integrated forecasts, you could also do this with this model now, but there's still a visible gap to the true model. And here, this is this part that I said I would talk later about. So before the very first cycle, right? Essentially this neural network that goes in here. So one problem a bit with this algorithm, which is a problem of all iterative algorithms, and this iteration here is with respect to cycles, you need an initial point for starting this. So you need an initial estimate of the neural network to estimate the dynamics. Yes, Eduardo?
So concerning this table that you have just shown, these are the errors concerning one time-step prediction.
No, these are the full analysis. So what you do is, let me quickly go back to this.
So it's the analysis state.
So what you do is you take your model and then you run ENKF on this, and this produces a full analysis state sequence.
Yeah.
From k equals k0, which is the beginning, to all the way to k, which in their case I think is 40,000. and then you average how close are you with your reconstructed states from the true states.
Yeah, I understand it, but the comparison is between, well, the time is the same in both, in XA and X.
Yes.
Okay.
So this is a measure not directly of the model, but the model in data assimilation.
Yeah. It's the analysis stage.
Yes.
It's not, okay. Thank you.
No problem.
Is it correct then that the analysis does not take into account any future observations, right? So the analysis of X at time, 500 takes into account essentially observations 1 to 500, but not 501 or further.
Yes, they're using an ensemble Kalman filter, not a smoother. The same authors have worked on smoothers, so naturally they mentioned the fact that you could use a smoother, but they choose not to because of speed.
Okay, thanks.
Again, just to stress, this general setup, as I think they also say again in the discussion very early on and very prominently, extreme flexibility. Yeah, a major feature of the proposed algorithm is extreme flexibility. A number of data assimilation techniques would work, and a whole number of setups for learning the dynamic also work. So Kalman filter, Kalman smoother. Principle for the var is another approach of doing data assimilation. A bunch of stuff would work. Okay, so this is the full spectrum of Lyapunov exponents that they learn. It's not perfect, but at least all the positive ones are captured very well by the model that they just learned from these noisy sparse observations. And this is an example rollout that we've seen in the beginning. And then one thing, or two more things that they really look at is what if you have different amounts of noise, and as you would imagine, the more noise you have, the worse you learn the dynamics. So this is noise on the observation sequence, and then the RMSEF, so the prediction error is on a model that is completely trained on data with this noise level. And if the data was very noisy, that's the violet one, then the model is very bad in the sense that the prediction errors relative to the ground truth Lorentz 96 dynamics, they rise very steeply. And if you had very little noise, you can reconstruct the dynamics much better. There's an argument about why the terminal, the asymptotic values are different, because the one that had a lot of noise, it actually tends to underestimate the variance of the Lorentz 96 states. So the state space isn't fully explored by these models. They're crunched towards zero.
So I read this and I found it very surprising and confusing. When they give the explanation, the emulators, the surrogates underestimate noise variance. It does seem to be what's happening here, but it's not really clear to me why that should be the case.
I'm afraid I also can't offer a very high quality intuition here.
It's clearly a robust finding, but it's a bit of a mystery, no?
It's interesting that I would have expected naively as well also that a really badly trained model might be prone to producing some bizarre extreme values, but apparently not.
Maybe it's something to do with overfitting during the training procedures? I don't know. Yeah.
Unfortunately, me neither. And then this is, I think, the final figure for this paper that we will look at, or maybe the second final. So this is then the other thing when you fix the noise level and you vary the amount of observations that you have. So this is 30% observed versus 100% observed and 100% observed with no noise. So this is the classical case, or what it means classical case, the simple case that we talked about. And this is going back to Toby's question, like, what is really the difference between first estimating the states? Why do you have to do this? If you had all of the states without any noise, this would be the quality of the emulator that you get. And then depending on how much you observe, even with this algorithm, it deteriorates quickly. There's a region where things work out quite well, up to, what is this, 50%. You roughly have a plateau, at least given this length of data, right? And then 40 and 30% really seem to break down. But again, it's a question of how long the state sequences that you train on. If you have a lot of data, not only 40,000 time points, but I don't know, 10 times that, then even 30% might work quite well.
Are these numbers somehow normalized? Because I was a bit confused when I saw this figure that when you have missing data, the model converges faster, and they kind of converge to the same point of accuracy. Doesn't this tell me that?
So the final Y level here is the forecast mean squared error of systems of dynamics that both stable, as they notice. So the original ones are, of course, but also the learned ones are stable. And what these root mean squared errors boil down to is, what is the typical system size for each of these models? So if you had a 1D system and your original system had values between -5 and 5, and your estimated system would have typical values on the long run between -3 and 3, then you would expect an error of up to 8. This is why this is bounded, right?
All right, yeah.
The more interesting thing is that, yeah, these things do not seem to explode, because also the learned system, even though it's learned from noisy subsample data, it seems to be stable. It doesn't seem to explode. This would really go up to infinity if over long simulations, the values would go to infinity of the system. But as you see on this color bar, it's kind of long-term stable. The system, it doesn't go, I don't know, plus minus 50 in the end.
Right.
Okay. Then there's one thing that's always interesting is how much data do you need? As expected, the more data you have, so this is forecast errors and the Lyapunov. So the mean squared error on the Lyapunov exponents, the better you can estimate the system. It's not night and day, so apparently 400 are okay, 400 data points are okay-ish to get an idea. But okay, these are single step. The blue bars are single step estimates. The more interesting thing are the orange ones, the Lyapunov exponents of the dynamics. And they seem to be not so terribly affected by, at least over this range. If you go to below 400, it's probably going to break down. And what was this one again? So this additive model error, they vary that one, which goes back to this, which actually I think in their case goes into the ENKF. So this is a hyperparameter of the ENKF, I think, if I'm not mistaken. So you have to check that one. So that would be it about the main paper. If there are any more questions, I don't think there's another figure. Nope, that was it. These are the authors. I would then rather quickly touch upon the second paper, which extends this in one or two particular ways. Okay, if there are no questions, I'm quickly gonna zoom back up here to the main figure. So this whole setup where you have an iterative algorithm where you're trying to estimate some parameters of a dynamical system through first estimating a state sequence and using that estimating updating your estimates of the dynamical parameters, That has been around in machine learning for a while. So for those of you who've looked into the second paper, there's this algorithm called expectation maximization, which goes back to Dempster et al. 1977. So it's been around for a while, and it's a general algorithm that you can use whenever you have these what I call latent variables. So in this case, this was the actual state. So you had the observed variables, which was noise corrupted subsample version, but you have these latent variables that are relevant for estimating the parameters of the dynamical system, but you don't have them, so you have to estimate them. And one thing I wanted to show very quickly before we go to the actual paper, the actual second paper from the same authors as the first one, is this classical paper. Goes back to 1996 by Zubin Garamani and Geoffrey Hinton. If you don't know these two people, Hinton is kind of like the godfather of neural networks. He's been working on neural networks since, I don't know, the 70s or 80s throughout. And Zubin Garamani is one of the leading scientists on integrating neural networks with probabilistic modeling. So he does a lot on Bayesian neural networks and that kind of stuff. But in 1996, they were both sitting in Toronto, working together, and they were doing this kind of EM algorithm with a very similar setup as we will see on linear Gaussian models. So they had the dynamics from, now it's T instead of K, but you have an XT in an unobserved latent state, and it goes to XT plus 1 through a linear operator and then some noise. And then you have an observation Y, which is an observation operator, now C instead of H, plus some noise. And what they did already back in 1996, through this EM algorithm, they explained how to learn these parameters A and C, and then also of the covariance matrices Q, sorry, this doesn't really work, but Q and R, from only observations of sequences of observations Y. So I'm showing this for two things. First of all, this whole idea of learning dynamical parameters from noisy, partially observed data in this kind of fashion is really not new. Originally goes back to 1977 and has been studied here for linear dynamical systems in 1996. But what I also want to show you is for those people who struggle, because I've already heard from one or two people, that the mathematics in the paper is fairly dense. I just wanted to show these equations, that what these four authors in the second paper that we're going to look at in a moment, what they actually derived is not in a vacuum. A lot of the stuff is indeed new for this particular application, but learning, for instance, the state noise covariance Q in such a system, there are good guidelines because people have worked this out for similar systems. So in the linear dynamical case, where in particular the hidden dynamics in state space are simpler because this is A is just the parameters of a linear operator, things are easier. You can do this whole thing, the maximization with respect to the parameters, you can do this closed form once you've done your Kalman filter to estimate the hidden state sequence. So it can be closed form, but it's still a maximization with respect to the parameters of the dynamical model, as we will see in the next paper. So just as you've seen this, that they're actually building on a very established theory of machine learning, how machine learning actually used to look like a lot before in around 2014, 2015, neural networks really took over the field. Okay, to the second paper, it's a very long paper, I know, and there are a lot of derivations in there, and I understand that not everybody is very, very familiar with probabilistic modeling, so I will just try to guide you through the main points. Okay, so there's follow-up paper which came out about 2 months after the first paper that we've seen from the same authors, just in different order, Bayesian inference of chaotic dynamics by merging data assimilation, machine learning, and expectation maximization. So the title already tells you we have pretty much the same ingredients: chaotic dynamics. We're going to look at Lawrence 96 again, data assimilation, and machine learning, which were the two building blocks of the algorithm from last time with an E and KF for the data assimilation and joining a neural network for the dynamics. And the new thing here is really this expectation maximization algorithm, which is like the original form of the thing in terms of probabilistic modeling. And so this is how these things are written down in probabilistic terms. I think the literature of data assimilation also expresses the problem, or likes to express the problem in terms of probabilistic terms. So the idea is that if you have a sequence of observations, and thankfully they stuck to the notation, so Y is still the sequence of observations, which may be noisy and incomplete, and from this you can estimate a sequence of hidden states through this Bayes rule. So what you need is you need a model of the observations given the hidden states, which is given by the observation operator H. You need a prior for the hidden states, which is going to depend on the dynamics. So a hidden state sequence is going to be likely if it, or probable if it, well, corresponds to the dynamic model, and, well, not if it doesn't. And then there's a normalization term where you actually need to integrate it out over all possible hidden states, which is in practice intractable. And what they do is they nicely map this onto the analysis and forecast step. So the analysis step is you try to estimate of a data analysis scheme, sorry. The analysis step is you estimate the current hidden state from the sequence up to now is, well, you estimate the current estimate of the state from the sequence up to the last point, and then you integrate the current data point, the current observation, and this is how you go always from k to minus 1 to k, and you kind of do one step at a time. And then forecasting, how you actually go one further step, is through this dynamics. Before they were mostly deterministic, where you went from xk to xk plus 1 through this neural network estimate. Now they're explicitly saying like this is a distribution. There can be noise. Okay, and what's the thing here now? Well, they make it explicit that there's going to be an estimate of the dynamics. So the idea is you have the observation of states, y from 0 to k, of the state of the sequence of observations, and from this you want to estimate, as before, both the hidden sequence and the parameters of the dynamics. And so again, these are going to be parameters. A are going to be parameters of the neural network. So what used to be W is in this case called A, and you make this modeling assumption that you might have a prior guess over what the dynamics look like. Given the dynamics, you have a good idea what the state sequence should look like. In a deterministic case, you know it exactly. In the stochastic case, you can still tell likely from, or probable from improbable state sequences given the current set of dynamics. And then when you have the state sequence and the parameters of the dynamics, you know how to produce the observations. And most of what they're going to be looking at in this paper is you don't even need the parameter A here. This is a general setup. It's in principle the same thing we've looked at last time, just not through this lens. So what you want to do in the data assimilation step, you want to estimate this sequence of states given the dynamics and the observations, and then in the optimization step, you want to optimize this function with respect to A given the state sequence and the observations. Well, you don't need the observations anymore. Okay, and then there's one more cool thing that they point out in this paper. So in the last paper, they learned this function, the state update function, from k minus 1 to k. It used to be called G, but in this case, it's called F. So the neural network was directly parameterizing this function. What you can also do, which is quite cool, is you can instead directly learn the differential equation. So in the Lawrence 96 case, it's this simple bilinear function that we've seen before. So you directly parameterize that with a neural network, and then you plug that into a solver, a numerical solver like Kronecker fourth order. You have a figure how that looks like. So now they have the same kind of neural network as before. So there's their batch norm layer, there's their CNN layer. This is the bilinear stuff, now shown slightly differently with the multiplication of some of these. And then there's the output. The only difference to before is that the output now is not directly the last state, as it was in the last paper, but it's the differential equation. And this differential equation, now you plug into, in this case, a second order Runge-Kutta solver. So the second order Runge-Kutta solver, what it does, it starts at the left of the integration interval. It takes the derivative at this point, and then it does an estimate with that, like an Euler update, what the state would be in the middle of the integration, and from there, from this point, it estimates the derivative again, and then it averages those to give you the actual update.
Marcel, we have another question from the Zoom chat. Tobias Finn asks if this is related to neural ordinary differential equations.
No,
it has a very, very similar spirit.
Yeah, so I meant with this that this is related to neural or ordinary differential equation. So it is.
Okay, it's not a question.
No, it was a comment.
Yes.
Yeah.
It is very related. The thing is that the main difference in interpretation, at least from how I understood it, is that you know that the system is a dynamical system. That what you're trying to learn is a dynamical system with a given solver. While in the neural ordinary differential equations case, you just have a black box mapping from X to Y.
Yeah, I think.
But it's a very similar spirit. And for those others who are wondering why we're talking about this, so neural ordinary differential equations was, I think, the paper of the year of the biggest machine learning conference 3 or 4 years ago, which had a very curious idea of rephrasing neural networks as dynamical systems. And instead of learning for a finite set of layers of a neural network, the weights, and then the input flows through this network from the starting point, which is the first layer, to the end point, which is this last layer. They learn a differential equation that gets numerically integrated from the first point, which is the first layer, to the last point, which is then interpreted as the output layer. Very cool concept, strongly related to this, but in a different context. Okay, so this is a different way of learning. Sorry? Okay, no, I missed it. This is a different way of learning a dynamical system with neural networks. You don't just directly parameterize the state update function, but especially if you know what is a good numerical solver for your problem, you directly target the differential equation and then use that solver. One of the nice things is that, and I've been working with this a bit myself, it seems to be way harder to make it unstable this way, because a numerical solver like Runge-Kutta is already designed a bit to be more stable than, say, an Euler update, right? Okay, then here again is the definition of our observation function. It's the same as before, just now written out. So this is Gaussian, some linear operation matrix H. One thing that is really new in this case, in this paper, which they introduced, which is maybe the main novelty here, is that they introduced this idea that there is noise on the state updates and that they actually model that. So you have the dynamics and you go from k minus 1 to k by applying the update function, which can now be directly parameterized with a neural network or through the differential equation. And then you have this noise covariance matrix that is not just the identity, and it doesn't come from a common estimate, but this will be directly a parameter that you estimate just as much as you learn the parameters of the neural network. In principle, these noise covariances can be time varying. That usually, however, means you can't learn it from a single observation sequence. Like if you had a so-called, what is sometimes called a trial structure, like you had many starts from the same initial state, you could actually learn them time varying. If you just have one, then what we will also do in the rest of this paper, you assume this to be constant over time. Okay. So this is the slightly more verbose problem that I'm now going to solve. I'm not going to try to read out this in the same way as I did before. The main thing is you're trying to estimate those two things. These are the dynamics now. So the neural network parameter for the dynamical model and the state update noise. And in order to get those two things, you will also have to get the state sequence. So the dynamical model that we now learn kind of like from scratch from data is going to have two parts, the neural network and the noise estimate. And as they really point out once they write out the loss, so this is the same function as above, so this thing here just plugged in. If you look at the form of this is really very, very closely responding to something that is called weak constraint 40-var in data assimilation. So one way to sum up this whole second paper is that they extend the approach from the last paper, which was very closely related to hard constraint 40-var to weak constraint 40-var by introducing these noise covariances. And then they go through a lot of stuff that I'm going to skip in the interest of time, but these are standard considerations from machine learning as you have them in textbooks. Like, for instance, if I have it open here, this is the Bishop pattern recognition in machine learning, which you can actually find online with a simple Google search. These kind of standard considerations, like how do you actually optimize these things, especially if you have these integrals in there where you, in this case, you want to integrate out all possible state sequences, which is actually non-tractable. So you use Monte Carlo estimates to approximate those integrals using samples. This is all fairly standard stuff. I'm quickly going to jump to the expectation maximization part.
Well, so before you go further, can I ask a question? So I'm sorry, sure. I'm just jumping in. I can't raise my hand. Apparently hosts cannot raise their hand in Zoom calls. But so you said that this is more weak constraint 40-var, where you have this kind of error term in the evolution of the model state itself, whereas the previous main paper was hard constraint. I thought the previous main paper was also weak constraint, but it was assumed that the noise, or rather the error in the model state evolution was known, that the Q matrix was known. Whereas here we're estimating it.
Yes, you're correct.
So this is just, it's basically a weak constraint, but it's kind of, they come up with tools to calibrate it and to use it in these non-toy model cases, perhaps.
Yes.
Okay, thanks.
Thanks for clarifying that. So if you want to do the EM algorithm, it consists of two parts that very closely map to what we've seen already in the last part, and it has to do with integrating out these hidden state sequences. So if I quickly go back to this last loss, if you want to have the probability of the dynamics and the noise updates, given the stuff that you assume you know, so this is the actual observation data, and this is what you know about the observation operator, then in these kind of latent variable models, you need to integrate out of all possible state sequences. Back in the day, sorry for that, back when we looked at the last paper, when we ran the ensemble Kalman filter, the ensemble Kalman filter actually returns an estimate of the distribution of the hidden states via the ensemble mean and the ensemble covariance. So over this over this probability distribution, if you integrate out this term over all of these states under that probability distribution, you get the left side. And the left side is what we actually want to maximize. Given the data and what we know about the observation operator, we want to have the most probable dynamical model and state noise covariance matrix. So given this integral, and solving this kind of problems is what EM was made for. You see this kind of integral in here, where you integrate out the hidden state sequence. And the way this operates, going into detail of why EM works would be taking another hour that I do not want to put you through. Again, I can point to this book, which has actually 1.5 chapters on it. There's one on the EM algorithm in isolation, and then there's one of the EM algorithm in particular in the context of these linear dynamical systems, from which, as I said before with this other paper, it is much easier to get an idea of what's happening in this nonlinear case. So the EM algorithm has 2 steps that map nicely onto what has been done in the last paper. And there's an expectation step where you try to get the expectation of the hidden states given the data and your current estimate of the dynamics. So this is where they are in the ENKF for. And then you have to integrate that quantity in here with respect to that integral. What is done in practice is you take a Monte Carlo approach where these different samples here with the superscript J, they come from the ENKF ensemble members. So this is how you do the expectation step that maps very, very closely to what was done before. And the maximization step, then you take this internal loss here, and then you maximize that with respect to the current parameters. And theta in this case contains both the neural network weights and this state noise update matrix. So this is pretty much the same stuff as we've had in the last paper, just written down properly in the most general terms for this extended case where you also learn the noise updates. And what follows is a bunch of considerations which you essentially always have to do when you do EM in practice on anything but the most simple toy problems. You need to think about how you actually do these individual steps. Like, how do you actually estimate the expected value? How do you actually want to optimize this loss? In particular, this loss is a loss in 2 very different kind of variables, the neural network and then the residual.
Marcel, your audio just cut out for me. I don't know for anyone else.
Yes, same here.
Marcel, if you can hear us, maybe try to adjust your microphone. If you want to, call me on WhatsApp or phone, I can patch you in via speakerphone. But I don't hear anything right now. I think he's restarting. Well, let me take over in the meantime. Everyone can hear me, yes?
Yes.
Okay. So I don't know.
Sorry,
Hi.
I lost connection.
Oh, okay, no problem. Oh, you want to take back over the screen share?
Sure. Really sorry this happened.
No problem. It
Also
wasn't bad at all. Can I stop sharing? I'm having some issues myself.
Sorry, I don't know where you lost me. I just wanted to say that there's this maximization step where you try to optimize numerically over the network weights and the noise updates. And there's several ways to do this. Either you do it both at the same time, with LBFGS, or you do a coordinate descent where you update them blockwise. They also have an approximate solution where you kind of estimate Q in a fairly cheap way already during the E step, which allows you to save on a bunch of memory writes because you don't actually need the full state sequence anymore during the optimization step. And then you just optimize this function, which is only a loss in the neural network. And this then is pretty much the same maximization step as in the last paper, where Q is fixed and you just optimize the neural network with whatever stochastic gradient descent. So they come up with these two algorithms. A nice thing about being Bayesian and being probabilistic is you can always write down prior beliefs over what you think would be good parameters for the neural network, or what would be good parameters for the state update function. You do not have to do that for EM. In fact, they do not even do this for the neural network, but this would be one way of fiddling, for instance, regularization for the neural network into this framework without breaking it.
Marcel, can I ask you to stop your screen share and start it again? I don't know if others can see the screen share. I can't, which means the YouTube can't.
Yeah. Okay.
Yeah, and maybe start it again.
Sure.
I am having some issues. Well, I am going to leave the call and join. It should be fine as your co-host. I'll be right back.
Okay. Yeah. So this is the first one is the same system as last time. This is a 40-dimensional one-level Lorentz 96. So these are the forecast errors. They run an ensemble, I think of 10 members. Also of the dynamics, so also the dynamics are not stochastic. Would have been good to include a reference to tell you how well it works, but you do see it stays close to the ground truth Lorentz 96 system for more than one Lyapunov time unit. Then here are the Lyapunov exponent values between ground truth, so this is in green, and the ensemble mean, which now in this case work pretty well. Also for the negative ones, so if we go back to the last paper, we saw that the negative ones were pretty badly off. So now with this improved scheme, where they do a lot more work, but to also estimate more parameters, and where they also parameterize the dynamics differently by parameterizing directly the differential equation rather than a state update function. So this whole thing seems to work a lot better. Here again is the power spectral density, which also seems to follow a bit better, even though it's difficult to compare given the scales are a bit different. Then another thing they do is they try this out on a model where the observations are actually a very strict subset of the full system state. So they decided to describe this in this very funky scheme. So for those of you who recognize this, this is a two-scale Lorentz 96 model, or two-level Lorentz 96 model, how it's sometimes called. If in your heads you translate this funky function in 29C and plug this into here, you get the same equation as we had before. So this is this bilinear term, and this is the exponential decay. I think this should be an x instead of a u, otherwise this makes no sense. And then there's this second layer of variables which is coupled to the first layer through this term. Essentially what it is you have the same system as before, now with 36 locations instead of 40, but you have extra variables which are taken to be unresolved variables. What they do with this system, they use it in the way that it is often used is, these unresolved variables, you don't give as training data to your algorithm, you just give the resolved ones. And what the unresolved variables do is they make the dynamics more complicated in a way that you then can no longer reconstruct just looking at the data that you have. So this is a case which is more applied, where you don't ever see all of the system states. Like, there are a lot of system states for which you never have any observations, and then they see how well it still works. And there are some systematic differences, like all of the Lyapunov exponents are off by what seems to be a constant factor. But overall, especially if you look at the climate, the power, spectral density, things still work even in this case. Yeah. Then I have a bunch of other tests where they go through different data set sizes, and I think then different hyperparameter settings, because the ENKF has a bunch of hyperparameters again. But going through these, I think, would be a bit too much detail and would require direct comparison with the other algorithm. So with this, I think I would wrap up. So to summarize, what we're seeing today was two different approaches to learning dynamical systems directly from noisy and incomplete data. The authors have, through one little detour, shown that with classical algorithms for machine learning, you can in principle do this. Also with dynamical systems. So especially the deterministic type of dynamical systems is something that is studied very, very commonly in machine learning. So the case where you have the noise, where you explicitly model the noise on the state updates, it's actually the default in machine learning as I know it, at least for these kinds of algorithms. So the classical way, or the older way from earth science dynamical systems, where you consider the dynamics to be mostly deterministic, it's actually the more special case here. But these frameworks still work. You can apply them. You can show that they also work for these chaotic systems. And you can do a good job at evaluating to which degree they work on these systems. There's a big question out of all of these papers, at least for me, is scaling to large systems, to very large systems. There's two positive points here, I would say, to make in case of good scaling. The first one is the architectures that they use, the neural network architectures. And that's a trick that will also probably work for very large dimensional systems, is this convolutional assumption that you have, in principle, a local function that operates on small parts of X that you just apply to all different parts of the state. In this case, it's just a convolutional neural network with essentially an input region of 5 for every output location. So it's a 5-dimensional to 1-dimensional mapping. Even if you increase the system state size from 40 to 4,000 or whatever, it would still be that way. So this way, it could really scale to very large systems. And the other thing that is a bit curious, which is in the discussion of the second paper here, is that seemingly the authors have so far not made use of any GPU acceleration for their studies. So there is still room, a lot of room potentially for scaling this up. This would be it from my side. If there are any more questions, or if David has another comment.
Thanks so much, Marcel. That was a really masterful presentation of pretty complex material, and I think you made it a lot more approachable. I have one or two little questions or comments, but I'd really like to hear much more from anyone on YouTube or anyone in the Zoom chat. If you have, we have time for one or two quick questions. So a quick comment I have while we wait to see if anyone's got something is, so building on what Eduardo suggested in the very beginning, this question of noise versus missing observations. I do feel that, and I think the obvious, when we say this might be useful for earth science, the obvious connection to me would be for forecasting in something like a weather model, where you have this kind of data assimilation scheme, and you want to do kind of short or medium range forecasts. And there, you know, the models really do have much higher dimensions than the observations. You observe, you know, whether it's radar or satellite or, you know, in situ observations of some kind, you really observe a very small number of measurements compared to the size of the system you're modeling. And so really, even their smallest observation sizes, 10%, are probably much too big if we want to make an analogy with weather forecasting.
Yes.
And I think on a semi-related point, when we talk about data assimilation, so they're using ensemble Kalman filters, and they point out correctly in the first and I think the second paper, you could use something else. In the second paper, they need the ensemble members. They need a set of samples of possible system states given the observations, not just the mean or the most likely one. And there they have the ensemble members. I'm personally skeptical that this, even in the case of Lawrence 96, is going to give a good estimate. You know, it has to be, to use an ENKF in this way, you're making an implicit assumption that the range of possible system states given the observations is something like a Gaussian distribution. And moreover, one you could represent with a small number of samples. So if it has multiple peaks or other non-Gaussian aspects, I wonder what the alternative is really here, and I wonder how good the ENKF is. They mention, you know, sort of in passing in some of the passages that, well, yeah, it's very difficult. If you go to a very big system, you'd have to use localization techniques, so representing the covariance, the uncertainty in terms of, you know, different local effects across the geographic extent of your space, and this requires careful tuning. I wonder if anyone has experience with this and could tell us just how difficult it is and how finicky it is. I know there's some expertise on that at HZG, also at people are using that extensively at the Max Planck Institute in Hamburg as well.
I can comment a little bit on this because my PhD thesis is about, or I'm currently working on strongly coupled data assimilation with ensemble Kalman filters. And yes, so for very high dimensional systems, localization is really needed, because of the low number of ensemble members. But I think it's so they are actually using the ensemble Kalman filter, but I think they could also use some kind of variational data assimilation, which would be then more like also using the EM algorithm for inferring the latent states, or for inferring the model state.
Yeah, that's an interesting point. So thanks, Tobias. I think, so certainly for the first paper and for the idea of estimating a single best state sequence together with your dynamics A and your model error matrix Q, that would work. But if they want to do the proper EM where they have a probabilistic representation of the states given the data, there I think the variational approaches would sort of fall short, no?
No, because the ENKF is an analytical solution to the expectation maximization algorithm for linear observation operator and Gaussian assumption, and so it basically there's, for example, so at the ECMWF they use, for example, an ensemble of variational data assimilation. So they for every ensemble member they do a variational data assimilation procedure, and then basically for almost or for every ensemble member independently, and then you get if you put in 50 ensemble members, then you get out 50 ensemble members.
That's true. So then the idea is really you're taking how are they getting these different ensemble members? Are you just using random initializations as they optimize for the initial state?
No, so basically in the variational data assimilation framework you solve almost the same equations as here in the EM algorithm, and then they have to do a trick because the prior covariance is so the covariance needed to get the prior term for the cost function. They estimate this with the ensemble, so with the prior ensemble, and then they actually do a maximum a posterior for every ensemble member independently, and yes, and so it is actually possible to get an ensemble out of variational data assimilation, but for sure it is much easier to use an ensemble Kalman filter.
I see. That's very interesting. I didn't know that. I suppose there still is an assumption of Gaussianity when you combine the different ensemble members.
True. But then it is so. But then it is actually for every ensemble member the maximum a posterior solution independently.
I see. That's very interesting.
But of course this is much more complex than an ensemble Kalman filter. So the ensemble Kalman filter is the cheap option.
Thanks. Eduardo, you have your hand up as well?
Yeah, I wanted to, first to thank Marcel for the very nice presentation, very deep. And also I wanted to just shortly comment on the question that you raised just a minute ago about the about the dimensionality of observations and the model variables. And indeed, in most of the cases, for instance, in weather forecasts, so the observations, the dimensions of the observations are much less than the model. But there are other applications. For instance, if you think on understanding or predicting long-term climate evolution, so you may hope that the climate of the Earth may be described by just a few variables, let's say the total ice volume, global mean temperature, ocean mean temperature, and so on. And in that case, it's the reverse. You have a lot of observations that at certain time scales are all driven by just a few hidden variables. So you may think also of setups in which that situation is reversed.
So are you talking about, for example, if you had a GCM at a course, say 100-kilometer resolution, but then you have, I don't know, satellite data at a very fine resolution in space and time, or am I missing the idea a little bit?
Well, that's not exactly what I wanted to say, but it points in that direction. For instance, a specific example, you may have a climate model, not a GCM, a climate model that is what the so-called intermediate complexity model, in which, for instance, the resolution is something like 20 degrees in the atmosphere. And the ocean is just represented by a zonal ocean. That's just an average of the basins, and you have only two dimensions, depth and latitude. So this type of simplified climate models that I use to describe the climate evolution at very long time scales, let's say the glacial, interglacial cycles, or millennial time scales, and so on. Nevertheless, they have to be fed, well, or calibrated with observations, so that in that situation, you have the dimensions number reversed to, for instance, in contrast to a weather prediction model.
That's very interesting. Okay.
Yeah, but but then you have a problem with the observation operator to define your observation operator, mapping from the intermediate model to the observations.
Yeah, exactly. I mean, that's what I wanted to raise that point, that the usual situation in which you have less observations than the dimensions of the model. I mean, it's the usual, I agree with that, it's the usual situation, but there are, at least in climate research, maybe in other fields of science, in which you have the opposite situation. There are usually models that try to describe the very long time scale or large scale evolution of a system in a reduced state. And then the idea that spontaneously comes now to my mind is if we would like to apply this kind of setup of a neural network and a common filter, if it is at all possible, perhaps the neural network could also include some sort of autoencoder step in which the number of dimensions is automatically reduced, something like that.
Yeah, but I mean the EM algorithm on its own is already like an autoencoder. So there is a relation between the variation autoencoder and the expectation maximization algorithm. So, but for sure it could be possible to use another kind of autoencoder to reduce the dimensionality.
Oh.
As I understood, Eduardo, if I may quickly chime in, is one thing you could learn, and I think I still have the screen shared, is if you look at this observation operator from the state into the observed, you could compress the state into an even lower dimensional state if you then learn a decoding as well. So if you have a 40-dimensional system that you observe, like the Lawrence 96, you don't necessarily need 40-dimensional latent dynamics, but you could maybe compress it to 5. And then you learn within but this is an extra step that you need to do. Within the observation operator, before you plug it in, you first learn a mapping from those 5 into whatever, or you completely relearn the observation operator. And then you could also do an autoencoder-like stuff where the operation operator is like your decoder. And in an EM-like algorithm, you don't actually need an encoder.
Yeah, I see. Yeah, well, yeah, something like that. That's what I was thinking. I don't know if that's the case, for instance, in the Lawrence model, but you may think of another type of model in which some variables are important for the short-term predictions, or for the predictions for the next time step, or just 5 times ahead, and other variables are more relevant for the longer-term evolution. And you may be just interested in that longer-term evolution. So actually, the number of relevant variables in the model is actually lower than the explicit number of variables.
Yes, in classical, like state space models, as they're called, which are like in a similar setup, like here. If we go to the Monte case where everything is linear, the dimensionality of these latent variables, like the states themselves, is usually a hyperparameter that you have to choose and optimize in many cases. Like if you have a 40-dimensional observed system, if you have little data, it might be better to actually run this completely black box algorithm in this case with just 5 hidden dimensions. If you can only estimate a 5x5 matrix from the data that you have. I mean, the one thing to keep in mind, so this might be actually, if you have problems with data size and so on, this might actually be really helpful to know that you can decouple the dimensions in the latent space where you have the dynamics from the observation. I just want to point out that one of the ideas behind this whole thing was to get a dynamical system estimate from data that you can kind of interpret and use. so this is maybe why they want to stick to the original space. Yeah.
Okay.
But yeah, I mean, if the state space is compressible, so the hidden variables x, and you don't really care so much for interpretability, but you just wanted to, do a good job at predicting, then yeah, you can, in principle, you can do this.
All right, any more questions? If not, let's say thank you very much one more time to Marcel. Thanks to everyone who joined. Thanks to T-Mobile for fixing my home internet connection because Vodafone really wasn't cutting it. And we will see you guys all in 2 weeks. If you have any suggestions for a topic, for a paper, or you'd like to present your own work for 5 minutes, just send us an email and let us know. Thanks, guys.